Well, good morning and happy Friday, everybody. This is David coming to you from New Mexico. Today we're going to talk about ocean currents. So let's review a little bit from last week's video where we talked about the wind. First thing was prevailing winds on the globe. The second thing was prevailing winds on the flat earth. And then the third thing I want to mention is the doldrums at the equator. And then let's remember from earlier videos, number one, most important, the oceans are not flat. Look it up, check the video, the oceans are not flat. And then also we have star trails. They circle counterclockwise in the northern hemisphere, clockwise in the southern hemisphere. They do a little both ways at the equator. You need to remember those things because of what we're going to talk about today. Here are what the prevailing winds look like in the globe Earth. You can see the change in the direction of the winds at different latitudes, which of course would be very difficult on a flat Earth. Notice right here, it's called the equatorial doldrums. Mariners back in the Columbus day were always worried about this equatorial doldrums, and in fact also the horse latitudes, because there was no wind there and they would get stuck. So they were very careful to avoid those areas. Let's remember also from last week, if the Earth does not rotate, then the atmosphere would only circulate between the poles and the equator in a simple back and forth motion. So last week we discovered that this cell is called a Hadley cell. Again, you can look that up. And so because the Earth does rotate, we have circulating air that's deflected to the right, both in the northern and southern hemisphere. And this deflection of these winds is called the Coriolis effect. This Coriolis effect, even though some of you flat earthers don't believe in Coriolis, obviously the little drain thing does not work. It is not Coriolis, but there is a Coriolis force, and it does affect many things in our atmosphere and oceans. Again, like I said last week, this is kind of what the winds would look like if the Earth were flat. Of course, it would have to be flat and rotating, I guess. But you can see it's just a mess. There are winds turning every which way, and very difficult to figure out how this works. I'd be glad to hear from somebody if you know better how this would work. I just don't see it. So now let's talk about ocean currents. An ocean current is a continuous, directed movement of seawater generated by a number of forces acting upon the water, including wind, the Coriolis effect, breaking waves, temperature, and salinity. So there are all these differences going on that cause the ocean currents. There are 5 major ocean-wide, I think it's called gyres. I don't know the exact pronunciation there, but I think it's gyres. A gyre is a system of currents in the ocean. So we have 5 of those: North Atlantic, South Atlantic, North Pacific, South Pacific, and the Indian Ocean. Each one of these is flanked by a strong, narrow western boundary current and a weak and broad eastern boundary current. And I'll show you what those look like. Here are the 5 major gyres. You can see immediately, let's take this North Pacific. There's a warm air flowing north. It warms the eastern coast of Asia, Japan, and you can check those. Some of these, like Japan, are very well known for warm waters. As it rotates north and comes south, again, this cool current cools off the coast of California, Alaska, Mexico, and so this part has very cool waters. And again, California is known for cooler waters in the ocean. Over in the Atlantic, we have the exact same pattern. We have this warm current, the Gulf Stream that flows north, warms the waters of the East Coast. So the East Coast has warmer waters. And then down by Africa, we have colder waters again. But the main thing to notice is that these currents are rotating clockwise. On the Indian Ocean, South Pacific, South Atlantic, same pattern, but they're rotating counterclockwise. And then lastly, we have this Antarctic circumpolar current that runs the entire length of the south part of the planet. Okay, this is my try at doing the flat Earth. I tried doing arrows, and I guess this one was halfway decent. But when I got to the Southern Pacific, you can see that this area is just gigantic, and I couldn't figure out how you could have a current that flows around this way, or I guess backwards around this way. Here's the North Atlantic, South Atlantic, and the Indian Ocean. And again, you know, if there's no rotation of the Earth and it's flat, then where in the world do these prevailing currents come from? How do they originate and keep going? In the northern hemisphere, let's look at all the things we've proven in the past few weeks. The sun appears to move east to west because the Earth rotates west to east. The moon also moves east to west because the Earth rotates west to east. However, the moon is moving west, so it appears to move slower. Star trails appear to move counterclockwise because the Earth rotates west to east. Ocean currents move west to east because the Earth moves west to east. This is caused by the Coriolis effect. Winds blow west to east because the Earth rotates west to east. You can check this on your weather. Watch your local weather in the next few days or weeks, and you'll see that primarily the winds move west to east. I see this all the time on my local news. And then if you talk about major weather systems like tornadoes, tornadoes always move from southwest to northeast due to the Coriolis effect, and they spin counterclockwise. So you remember that we have ocean currents, winds, tornadoes all moving counterclockwise in the northern hemisphere. In the southern hemisphere, the sun also appears to move east to west because the Earth rotates west to east. The moon moves east to west because the Earth rotates west to east, but the moon appears to move slower because of its own rotation. Star trails appear to move clockwise because the Earth is rotating west to east. Ocean currents move east to west because the Earth rotates west to east. This is the Coriolis effect again. Winds blow east to west because the Earth rotates west to east, and this is because of the Coriolis effect. Lastly, I want to talk about hurricanes because these are not typical weather events. The first thing I want you to notice, and I'll show you, hurricanes almost never cross the equator. Remember this doldrums that we talked about. If they ever do cross the equator, I think there's been one or two in the history of recording earthquakes. When they do, they fizzle very quickly. Hurricanes always spin counterclockwise in the northern hemisphere and clockwise in the southern hemisphere. If you think there's a pattern there, it's because there is. Here's a map showing every hurricane since they've been recording. You can see clearly the motions here and here. It doesn't show the rotation, but you can look up individual hurricanes and see the rotation. But obviously, clearly, there is no hurricanes crossing the equator. I hope you take note of that and remember, hurricanes don't cross the equator. There is no reason why that should happen on a flat, motionless Earth. It just can't happen. The southern hemisphere should be equal to the northern hemisphere. There should be no difference in the way these hurricanes work. So let me close with this. Flat Earth is just a mess. Not one of these things would work if the Earth was flat and motionless. Nothing. So we're talking about the sun, the moon, the planets, winds, the jet stream, ocean currents, the different sea levels in the different oceans. All of those work because the Earth is a globe and it rotates. So that's all for today. I look forward to seeing you again next week.